All right, today we're going to go into more on Laplace transforms and where they come up, or we're not necessarily going to do where they come up, but we've already kind of discussed that and the point of them. But now we're actually going to do Laplace transforms of different functions and kind of see how you get these general cases that you can then use to piece together these bigger problems. So, just again, the definition of what is a Laplace transform. It's always this integral, 0 to infinity e to the negative st, times the function you're doing the transform of. And then with respect to t. Because the whole point is that this is going to take a function in the t domain. Because you do the integral with respect to t, it will take out any t variables. It takes out any t variables and just only leaves you with s. And then the whole point is you do the transformation, you solve it like algebra, and then you're going to do the inverse Laplace transform. So let's start with these. So what is the Laplace transform of e to the t? We'll start with the easy one. So the integral from 0 to infinity, e to the negative st times e to the t dt. Use our rules of exponentials. This is going to just be, I could say e to the negative st plus t, or I could just factor out the t and get, instead of negative s, I'm going to rewrite it as 1 minus s dt, which would give us 1 over 1 minus s e to the t times 1 minus s. Evaluate from 0 to infinity. Now we're going to assume this stays a negative coefficient for here. So we can say that this first part goes to 0, and then we just get minus 1 minus s. But instead of leaving it like that, I'm just going to distribute the negative to the denominator. I'll get 1 over s minus 1. Pretty straightforward for this first one. So then what if I did e to the negative t? Well, the only thing that's going to change now is this is going to be a negative 1 as opposed to a positive 1. So that means whenever we would go through and do the distributing the negative, that would become 1 over s plus 1. And then if we did e to the 2t's Laplace transform, this would just be 2 minus s, which means we're going to have 1 over 2 minus s e to the t 2 minus s, which is going to give 1 over s, not plus, 1 over s minus 2. And I think you see how it goes from here. Minus 5 plus 5. Positive pi, negative pi. Positive square root of 2, negative square root of 2. This one would just be 1/2, so this is 1 over s minus 1/2. So in general, the Laplace transform of e to the alpha t is 1 over s minus a. So if you think about e to the 0 as kind of the quote-unquote center, then e to the alpha t, you can think about multiplying t by some constant is the same as doing a horizontal shift of that Laplace transform. And these relations will become very useful later on. We'll use them to kind of lend some other ideas to the Laplace transforms and how we can use them. So that's the first one to tuck away. Just L, the Laplace transform of e to the alpha t is 1 over s minus a. And it's just like a shift. So we did these. Now, let's say you were trying to do the Laplace transform of cosine of 2t. It's not pretty. But Thomas Calculus does have in the large table of integrals, I believe in the back of the book, what this transform is. And of course, this would be one that you could look up as well. But what happens when you evaluate it? Well, as it goes to 0, or as it goes to infinity, you would get let's see. Well, as it goes to infinity, this goes to 0. This goes to infinity, but this is going back and forth between 1 and negative 1. This is stuck between 1 and negative 1. But this is technically this whole thing over s squared times e to the st. So the first part's going to go to infinity really, really fast. And then what about if we... Or sorry, I said that wrong. I was treating s as if it was a variable. T is the only thing that's changing. So again, you assume this throws it into the denominator. So these cycle only between 1 and negative 1. Technically, this goes between s and negative s, and this goes between 2 and positive, or in negative 2, sorry. So the first part still comes out to 0. But then when you plug in t is 0, you get minus 1, because it's e to the negative s times 0, s squared plus 4 times negative s. Cosine of 0 is going to be 1. And then sine of 0 is 0. So this comes out to be s divided by s squared plus 4. So the Laplace transform of cosine of 2t is s divided by s squared plus 4. So you could kind of guess just from looking at it, you can have a general idea as to what Laplace transform of, say, cosine of 3t might be, or 7t, something like that. You would have the idea. Sine's going to be slightly different just because the integral's not going to be the same. You could get it pretty close because you can think of cosine and sine and how they're related. But the nice thing is, I mentioned this last time, integrals are linear. So the Laplace transform, by definition, since it's using integration in the way it does, would also have to be linear. And pretty much same proof I did last time. Laplace transform of alpha f plus beta g. Factor out your constants because they're integrals. Integrals split over a sum. And now you have the definition of a linear function. And so what we're going to do is Laplace transforms, we'll just do those basic operations and just do a linear combination of them. So now if I wanted to find what's the linear or the Laplace transform of negative 11 plus 5 e to the negative t plus 3 cosine of 2t, using our previous information, we know this would end up just being negative 11 over s, because you would factor out the 11. And this is like doing the Laplace transform of 1 times the negative 11. This would be 5 over s plus 1. Because again, constants get factored out to the front. And plus 3s divided by s squared plus 4. So Laplace transform, pretty easy to get back to. Or pretty easy to do over a sum. So here's a general table. Sorry. Here's a general table of kind of your basic and most useful Laplace transforms. So notice the difference between sine and cosine. Cosine had s in the numerator. Sine has b in the numerator. T to the n actually has a factorial, which is kind of interesting. And then some combinations of e to the alpha sine of beta and then e to the alpha cosine of beta kind of pop up in very interesting ways. But this table's in the book, and it's pretty easy to go back or relate to. Or not relate to, but pretty easy to read. Now, this is why I said this is important. Because if you have this table and you know what Laplace transforms are, say when we had done the previous problem, or not the previous problem, the problem in the previous lecture, and you had that table in front of you, you could look at it and go, oh, that integral is that thing. So what you could do then is just say, well, now because I know what this integral is, I can actually work backwards. So you can do the table from right to left to get back to your t domain from the s domain. The inverse Laplace transform gets you back to the answer you were actually after. Because we're dealing with things in the t domain, you map them into the s domain, treat it like algebra, and then bring it back. So that's why you would want to use Laplace transforms. So piecewise continuity is kind of an interesting thing. So and basically it's just kind of a rule to, I don't know the best way to put it. It's just a rule to basically eliminate the discontinuities. So a function f of t is said to be piecewise continuous on a finite interval if f of t is continuous at every point except possibly for a finite number of points for which it has a jump discontinuity. So specifically, it has to have a jump discontinuity. Now that's really kind of interesting that you call it piecewise continuous if the only problem it has is there's a jump. Not that there's a vertical asymptote, just that there's a jump. And then it's piecewise continuous on 0 to infinity if there's a point where it's continuous on a closed interval. So, and then for all n greater than 0. So basically, you can find piecewise continuity throughout. So infinite piecewise continuity and things like that. So even if you were to so these two functions are pretty easy examples. There's one discontinuity here that t equals 5. That's our only discontinuity. So it has a finite number. So it only has one discontinuity. So the answer to that is yes. Then this function would also be piecewise continuous because it's only discontinuous at t equals pi and 3 pi. So we have two discontinuities. So even if you take a function like, say, let's say we were trying to now look at this one. What if I said f of t was equal to 1 over sine of t? That in all reality has an infinite number of discontinuities. But based on the piecewise continuity definition, because I can make finite intervals where there's a number of places where, or I can make intervals where it's piecewise continuous, and it only has a finite number of jump discontinuities. Well, sorry, this one was a bad example. This one is technically not. So this one's not piecewise continuous. And the reason for that is it doesn't have jump discontinuities. It's completely undefined at 0, pi, 2 pi, 3 pi, 4 pi, and so on. Those are not jumps. Those are just straight up discontinuities. There is no point there. Versus if you were to take, say, the ceiling function, which, remember, ceiling function just takes whatever the value is and rounds it up to the nearest integer. This is going to look like 1, 2, 3, and you get the idea. That one's going to have a finite number of jump discontinuities on certain intervals. Even if your n is 18 million, there's only 17,999,999 jump discontinuities. It's still a finite number of them, so it meets the definition. 1 over sine of t does not meet the definition because those are not jump discontinuities. Those are just discontinuities. It's not like the t minus 5 absolute value over t minus 5, where even though it's not technically, or it's technically, if you looked at it, you would just go, oh, it looks undefined. It's not really, because it's a piecewise function. So, or because of the way the piecewise function works. Now, even piecewise continuity kind of implies that there's a piecewise function. You could technically rewrite absolute value of t minus 5 over the point as basically just like it's less than 1 at 5 and greater than 1 after 5. So you could rewrite it as a piecewise. Sine over t, you can't really rewrite as a 1 over sine over t, sorry. You can't rewrite as a piecewise function. So kind of the giveaway is also in the name, that if it's part of a piecewise function, you should be able to get piecewise continuity out of it. Now, let's say you have f of t is what they refer to exponential order. And this is kind of like a bounding theorem, to where you say a function is of exponential order, alpha, if there exists an m and a t such that the absolute value of the function is always bound by m times e to the alpha t for any t past a certain point. So it's one of those theorems that you can say, okay, it may be sporadic at the beginning, but eventually it will level out. which also means you can kind of rewrite the theorem to say that there exists a beta such that the limit of e to the beta t is finite, because rewrite this one. Because what I'm saying is at some point t, every t past this will make the function less than or equal to this side. So what I'm saying is that if I do the limit as t goes to infinity, because with infinities, we don't really have to worry about the previous parts. We know eventually it works, so just say it keeps going on and on. Divide the e to the alpha t, because we're typically not trying to get e to the alpha t to be negative. So typically you want to think of alpha as a positive number. So less than or equal to m. So m is just a constant. And it's a positive constant. So now the reason I say a positive constant is you kind of can look at it and go, well, if it eventually, like, the limit goes to 0, then you can say, okay, maybe there's a finite number where this works. So like if I do sine of t, don't try and think about it as I need to find a constant m. Just look at it and go, okay, well, what do I know about sine? So I'm going to do limit absolute value of sine of t divided by e. I'm just going to start out with to the t. Then I know eventually, so at 0, I know technically sine of t is always going to be less than 1. So then I know as t goes to infinity, this is going to go to 0. Now notice that I could technically say this is less than 1. I could say it's less than or equal to 17. I could say it's less than or equal to 170. But the key thing is this limit goes to 0. Now notice, though, I didn't say the limit had to go to 0. I just said it had to be finite. This is less than infinity, so it meets that definition. All right, now what if I'm dealing with the absolute value? So the limit is t goes to infinity of sine of 3t times e to the 3t. Now what do I need to divide it by? Well, I just need the limit to be finite. So what happens if I divide it by e to the 4t? That would give me limit as t goes to infinity. Oh gosh, I forgot how to draw. Or write, sorry. T goes to infinity. This would be sine of 3t. Because the absolute value technically doesn't apply, or not that it doesn't apply, but we don't really need it for e to the 3t. So if we get e to the 4t, this is technically going to be minus 3 to the t. So I'd get limit absolute value sine of 3t divided by e to the t. We then know that would go to 0. So I want to work with these last two. If I try and say just t cubed, then that one's pretty obvious that I can just divide that by e to the t. Because eventually an exponential is always going to outrun a polynomial. That's just kind of how the way things work. Because it's much more efficient to multiply the same number by itself. So this is going to eventually give me 0. So you can say yes. This one is where things get tricky. Because what if I try and do, now I've got e to the t cubed divided by e to the alpha t. Then we kind of run into an issue, and that issue is kind of like in the same way exponentials typically outrun polynomials. Most of the time, sorry. I'm brain farting on the last one. Let me do these in a different order. Because eventually, even though you may be doing a billion times 2, a billion times 5, a billion times 7, eventually, once you kind of get past that alpha, you're going to be doing a billion times a billion times a billion. So this one is always going to be going towards infinity. So this one's a no. So then you get to the question, so 2, and this will become 4. This will become 2. This one's 8. And then this one's 9. And then this is 16. And then this is 16. This is why I had to switch it. Because there's a point where they trade out. And then there's a point where it is more beneficial to kind of keep that idea of trade the value, or it seems like it's better to do e to the x squared or something like that. It seems like you might be better off going, oh, well, what if I just keep raising larger numbers to the same power? But the difference is I'm getting more numbers that are I'm getting the same number and getting to multiply it more times. And that e to the alpha t, you would be able to pick an alpha large enough to make this work. I probably just talked about this for way more than I actually needed to. I might end up cutting this out or just trimming it down a whole lot. Well, I guess you'll find out if it's still here. So, what makes a function have a Laplace transform? So take a piecewise continuous function of exponential order. This is why they introduced those two things. So if it's piecewise continuous on 0 to infinity and has some exponential order alpha, then the Laplace transform of f exists as long as s is greater than alpha. So pretty obviously, you can see where this comes into play for the piecewise function. So 4 is always going to work for alpha equal to even just 0.1. Sine of t, you could use 1. E to the 2t probably would be best to just actually use e to the 2t. Because it's piecewise continuous, because it's only got a finite number of discontinuities. And you could do the the exponential order test for each one, or each component. So then if you do the Laplace transform of each individual component, again, just use the pieces that we have. And this is where something interesting will happen due to the nature of these problems. So remember the original Laplace transform of f goes from 0 to infinity. Then we have e negative st, f of t, blah, blah, blah. But notice here, because we have to break it up into the piecewise components, kind of like with the original example. Now, instead of this going from 0 to infinity, it has these little stopping points. And those stopping points actually have an interesting effect on the solution. So you do all the algebra. And what you find out is, so notice we have our 4 over s, which is the kind of first part of the Laplace transform. But notice you kind of link them together. There's a discontinuity between sine of t and e to the 2t. At 3 pi, what happens? Here's 3 pi, e to the negative 3 pi s. And here's the Laplace transform of sine plus the Laplace transform of brain work, the Laplace transform of e, with this little 6 pi in there because it's not just e to the 0. And then there's a discontinuity at pi. So then you notice this one is negative Laplace transform of 4 minus Laplace transform of sine. And then you have the e to the negative pi s. So you have exactly where they connect together. So those points of discontinuity actually appear as your coefficients for the exponentials. So that's what's going to happen, is the Laplace transform is kind of going to, where there were discontinuities, it reconnects those functions together and then makes it a lot easier to deal with. So it's kind of like, either if you want to think about functions like paths that have shifted, it will readjust the landscape to make sure those points can meet. And it has a very interesting way that actually shows up in the Laplace transform of patching up those holes, or not holes, those jumps in the original functions. So 7.1 was, why do you need a transform? 7.2 was, how do you take a Laplace transform? What are some common ones? And then you can kind of guess with 7.3, we're going to actually kind of do a few more Laplace transforms, and we're going to kind of get into them and the usefulness a little bit more.